refraction at plane surfaces. Okay. Now the next topic that we are going to see is called as apparent depth. So write down the heading as apparent depth. So the meaning of this is, let's say there is an object which is placed in a denser medium. Okay. Let's say there is an object which is placed in denser medium at a depth h. Okay. So this is the object. And you're seeing from here. This is where your eye is placed. Okay. And you're seeing from here. Now the question is, will you be able to see the object exactly at point O, or will it be shifted from its position? Okay. That's what we need to answer. Sorry.
The position will be shifted.
Shifted, yes. So that shift is what is called as this apparent depth. We'll see what is a shift actually. Okay. So how do you know it will get shifted? So we need some supportive diagram to show that, right? So let's say the object has the tendency to illuminate, means it can send out light. Then we can take one of the incident rays to be in this way. I will take the incident ray to be in this way, such that there's going to be the angle. So what is the angle of incidence of this ray?
0 degree.
0.
It is 0 degree. So it is 0. So the angle of refraction will also be 0. So let us consider an other ray which is incident on the surface in such a way that if I take this as the angle of incidence, then the angle of refraction will be like this. So when the ray is bending from denser to rarer medium, so when the ray is traveling from denser to rarer medium, what is going to happen? It bends
away from the normal.
Away from the normal.
So that's what has happened, right? So what exactly has happened? I'll draw it more precise. It would have got bent away from the normal. So this is going to be R, right? I hope this is clear till this step. Now, tell me, the first incident ray, the first refracted ray is traveling without any deviation because the angle of incidence is going to be 0 degrees. Right? When you apply Snell's law, mu1 into sine I will be equal to mu2 into sine R. When sine I is 0, sine R will also be 0. That is the reason why it is going without any deviation. Now the question is, will the two refracted rays be able to meet on a real time? So are they getting converged or diverged?
Converge.
Diverged. So what should happen? You can only have a virtual image that is being formed, right? So this is going to be the virtual image. Am I right? I hope you are able to understand till this step. So when you elongate it in the backward direction, this will be the point where the image is formed. Means this depth is going to be h dash, and this depth is what is called as the apparent depth. Okay. Then what we can write is h is called as the real depth, h dash is called as the apparent depth. Okay. Then OI is called as apparent shift. So that is the shift that has actually taken place between the object and the final image. I hope you are able to understand. So this is going to be the ray diagram. So I'll show you the ray diagram here also. See, you're able to see this, right? So object is placed at a particular depth. Let's say the depth is D. Okay. And when the final image is formed, let's say at O dash, then the depth is going to be D dash. Okay. Delta X is called as the apparent shift. I hope you're able to understand this diagram. Yes or no?
Yes, sir.
Yes, sir.
Okay. So we will proceed with the derivation. So this is angle I. Let me take another color. If this is angle I drop a perpendicular. Okay. So I'm taking this as A and this point as P. Then if I take the triangle OAP, observe. If I take the triangle OAP, then what is angle OPI? This angle is I, right? Then how much will this angle be?
I.
It is alternate interior angle. It is going to be A. When this is R, how much will this angle be?
R.
You have elongated the same ray, no? So this will also be R, corresponding angles. I hope you're able to understand. Right? So what was the assumption I told you on the other day? You need, in this chapter, whatever angles you're going to take are going to be small. There is a reason for it. What happens is, if the rays are getting diverged a lot, you will not be able to see a clear image of this particular object. Means you will not be able to see it as a distinct image. So for that, what should happen is, angle I and angle R will be very small. So when the angles are small, what is the approximation we can do? Sin I is approximated to I. It can also be approximated to tan I. Similarly, sin R will be approximated to R, which is also approximated to tan R. I hope it is clear. Right?
Yes, sir.
Okay. Now tell me one thing. Wherever in this chapter, wherever you need to involve sine of an angle, what comes to your mind? So wherever you need to apply sine of an angle, what comes to your mind?
Snell's law.
It is Snell's law. Very good. So since I am saying that sin I is going to be very small, first let me find out what that sin I is. Applying Snell's law at which point should I apply?
O. O.
It is at point P. So you should always apply Snell's law only at the point where the refraction is taking place. At O, there is no refraction. There is an object, that's it. So Snell's law should be applied on a point which is separating the boundary, which is separating the two media. So applying Snell's law at point P, what can we say is mu into sin I will be equal to sin R. Accepted? So refractive index into sine of the angle of incidence is equal to sine of angle of refraction, right? Which implies mu into, when it is approximated, sin I can be written as I, or I can also approximate it to
R.
tan I.
Okay, tan.
Will be equal to tan R. What is the reason for it? You already know this, right? So why I wrote it in terms of tan is because in this case, what is that I need? I need depth. So I'm telling you two logics, remember, okay? So remember these two logics. In this chapter, not only with respect to derivation, when you're solving a problem also, wherever you need to find angles, okay, most of the angles can be found using Snell's law, because that will be in the case of refraction. I'm talking in the case of refraction, wherever you need to find angles, you need to apply Snell's law. Wherever you need to find distances, okay, wherever you need to find distances, especially with respect to point objects. Here, what kind of an object am I using? O is a point object, right? So apparent depth is a distance. So if I need to find the distance, you need to apply the formula for tan. Okay. So when I'm saying tan, you need to start looking for right angle triangles. That is what I'm trying to say. Am I clear till this point? Now see. So if I take the triangle, so how many right angle triangles are able to see? Two, right? So what are the two which will involve I and R?
OBP.
So from triangle OBP, what can you conclude? You can find tan I. So what is tan I? What is tan I, guys?
BP divided by OB.
BP by OP.
That's right. BP divided by OB. So what is BP? Okay, BP is
H.
more. No, BP is not H. BP is some distance. We don't know what it is. But BO is going to be H. I hope it is clear till this point. Similarly, from what is the other right angle triangle you are able to find? Triangle
OAP.
B, BIP or IBP. Because I told you need to involve angle R. You're able to see the small right angle triangle. I'll mark it with red color. You're
Yes,
able to
sir.
see this? Yeah. So triangle IBP, what can you say? We can find tan R. What is tan R? BP divided by BI. So what is BP? That's the same. BI is going to be H dash. Right? So let me call this as equation number 1, equation number 2, and 3. So what I'm going to do is using 2 and 3 in 1, what do we get? Mu into tan I. In the place of tan I can write it as BP by H is equal to tan R. That is BP divided by H dash. This and this will get cancelled. From this, we can conclude H dash is equal to what? H divided by mu. So this is a very, very important relation, and there are many problems asked on this. Okay. So what we are trying to say is apparent depth is equal to real depth divided by mu. That is the refractive index. And remember the derivation, remember the condition under which this derivation has happened. Okay. So if they twist the scenario, you're not supposed to use this. When can you speak about apparent depth? Only when the object is placed in the denser medium and the observer is in the rarer medium. Please make a note of it. You can speak about apparent depth only when, what scenario? Can you repeat it? When the object is
Denser medium.
In the denser
Object is
medium,
in denser
observer
medium.
and the rarer
An
medium.
observer in the rare medium.
Make a note of it. Okay. It is then you can speak about depth, or else there will be something called as apparent height, which is not there in your syllabus. You need not worry about it. That is, if you interchange it, things will be different. So questions are based on apparent depth only. I hope the derivation is clear, right?
Yes, sir.
Yeah. So apparent depth is real depth divided by mu. This is the formula that you are going to use. There are many problems in NCERT also in the exercise. So solve them in practice. Okay. Now I'm going to talk about shift. So what is the apparent shift that is taking place? I'll call it as delta H. So what is the apparent shift that is taking place? So shift is OI. OI is nothing but OB minus IB. So what is OB?
Real
OB
depth.
is H minus, what is IB? It is apparent depth H dash. So H minus H divided by mu, that is H into 1 minus 1 by mu will be the formula for apparent shift also. So this is there is another important expression to be remembered. Okay.
Sir, can you scroll it up, sir?
Yeah. Shall I move on?
Yes, sir.
So this is all about apparent depth. So this is done. We have seen what is apparent shift also. Then the next topic that we are going to see is total internal reflection. Write it down. So write down the heading as total internal reflection. So I've heard this term.
Yes, sir.
Yes, sir.
So total internal reflection, in short form we call it as TIR. What is this actually? So here, if you observe one important point, we are talking about reflection, but why are we discussing about reflection under refraction? Okay. Next important question is, what do you mean by this internal? And why are we using the word total? Why are we not simply calling it as internal reflection or simply reflection? We are calling it as total internal reflection. Why so? Right? So let's try to find the answers for this. Now, certain important questions to be asked are. So before you proceed with this topic, there are certain prerequisites. You need to have an understanding of how the ray bends from one medium to other. So ray, I will put it like this. Incident ray and refracted ray. Rarer, denser, what will you say? So rarer to denser medium.
Then towards the
normal.
Towards the normal, a known fact. Denser to rarer, away from the normal. So this is also a known factor, right? Now let's see under what scenario this total internal reflection is going to actually occur and why is it so. Okay, let me take the first scenario. That is, I have a boundary. The boundary is separating which two medium? mu1 and mu2. I'll call it as rarer and denser, right? So when there is a light ray which is incident on the boundary which is separating the rarer and the denser medium. So first step is I'm going to draw the normal. So this is I, right? So I hope it is clear till this step. Now, see, this would have been the actual path. I'm using the red color one for the actual path. And the ray will start bending towards the normal. So this is going to be R. Is my diagram clear? Are you able to understand this?
Yes, sir.
Yes, sir.
Now I have a question. Okay. Let's say I1 for the time being is 30 degrees. Then what will be the angle of refraction? According to the logic that we see, it should be something less than 30 degrees, right? Now from I1 being 30 degrees to, if I increase it to, let's say, 45 degrees, then what do you think will happen? What do you think will happen with respect to the angle of refraction?
increases.
Will further decrease.
The angle of refraction, will it be less than 45, less than 30 also, or what will happen? So what do you think will happen? So what proof do we have in our hand? Only Snell's law. If I take this as mu, whose value is going to be greater than 1, if I take mu r to be 1, means I'm considering it as air medium, then mu r into sin I will be equal to mu into sin r. Accepted? So mu r is going to be 1 into sin I is equal to mu into sin. I don't know what that angle r is. Sin I is how much? 1 by root 2 is equal to mu into sin r. So sin r is equal to 1 by root 2 mu. In the previous case, what would have been sin r? If I take this as I1, I2 and R2, I2 and R2,
1 by 2 mu.
1 by 2 mu.
So 1 by 2 mu. Now tell me which one is less.
Sin R2.
Sin R2.
See, sin R1 is 0.5 divided by mu. Sin R2, from RMS value, we know that 1 by root 2 is 0.707 divided by mu. Means what is happening? Is it increasing or decreasing?
Okay.
Increasing.
So it is slightly greater than this value, right? Okay. So what will happen is, this is R1, this will be something like R2. Now my question is, if I keep increasing the angles, is there a possibility for me to bring this refracted ray closer to this boundary? That is the question.
Yes, sir.
Yes, sir.
Is it possible? Okay, let me do
Yes,
one
sir.
thing. Let me say mu is, wait, there is a small mistake. If I take mu is equal to 2, then how much is this going to be? 0.25. And sine R2 will be how much? 0.3 something, right?
85.
So 0.3 means R2 should be greater than R1. Yeah. So what is going to happen when the ray is traveling from rarer to denser is, there is no possibility for you to bring this ray, the refracted ray, closer to this boundary. Okay. How much ever you increase, the angle will always lie between whom? The angle will always, though the value of R1 is greater than R2, but what will be the restriction it will have it with itself?
Will not cross the actual path.
It will not cross the, it will not cross the actual path. The maximum actual path that is possible is you can make the ray graze along the surface. Means what should be the angle of incidence?
0.
0.
No,
90.
it is 90. Grazing along the surface means 90. Moving along the normal is 0. Grazing means moving along the boundary. It's called as GRAZING. They use this word a lot, especially in the case of prism. Okay, I hope you're able to visualize. When this kind of a scenario is happening, I'll mark it with a green color C. I'm using green color C. When this kind of a scenario is happening, what will be the angle of refraction? It will be something like this. Right. Now my question is there a possibility where when the ray is traveling from rarer to denser medium, I'm repeating it, is there a possibility where you can make the incident ray reflect back into the same medium when under the scenario when it is traveling from rarer to denser? What do you think is the answer? Tell me one thing. I'm asking the question again. When the angle of incidence is 90 degrees, I'm repeating the question. Angle of incidence is 90 degrees in which medium?
Rarer medium.
Rarer medium. Then what will be the angle of refraction?
0 degree.
It will not be 0. It will be less than 90 degrees because what is the rule we are trying to say? The ray will always bend towards the normal, meaning the ray will always be lying between the normal and its actual path. You are able to see the dotted lines that I'm drawing now? The dotted lines which I drew is the actual path, but this would have been the refracted ray. Are you guys able to understand? So you from 0 degree, even if you start at 0 degrees, you go till 90 degrees of angle of incidence. What is happening when the ray is traveling from rarer to denser? It is always bending towards the normal, means it is always, the refracted ray is always in the denser medium. Is there any scenario where the refracted ray is entering back into the rarer medium?
No, sir.
No, right? So what we are trying to say here is, in the case when the light is traveling from rarer to denser medium, there is no question of reflection. Then what should happen? Then what exactly should happen? We have to try the other scenario and see. When you try the other scenario, for example, see. Now you will have a clarity. Observe this. This is the boundary. Ray is traveling from denser to rarer. Refractive index of denser medium, I am taking it as mu, and the refractive index of rarer medium, for the time being, I am taking it as 1. Now, what is the angle of, if I call this angle of incidence as I1, then this would have been the actual path. What would have happened to the refracted ray?
Ends away from the normal.
Away
Away
from the
from the
normal.
normal means, in this scenario, is it going to be clockwise bending or anti-clockwise bending? Answer that.
Clockwise.
It is going to
Clockwise.
bend. Yeah, that's right. It is going to get bent in the clockwise direction, R1. Right? Now, if I increase the angle of incidence, let's say to I2, then what would have happened to the angle of refraction?
It will bend more.
Increase a little bit.
It will increase for sure. So here it is increasing in such a way that the ray is being pushed away from the normal. So when the ray has the tendency to being pushed away from the normal, can I say the ray is getting bent more towards the boundary?
Yes, sir.
Yes, sir.
Yes. Now we are able to relate it to the previous case. So what happened in the previous cases? It is always an anti-clockwise rotation. Whereas in this case, it is a clockwise rotation. So will there be a scenario that is going to be possible? That is, if I choose a particular angle of incidence in which medium?
Denser medium.
Denser medium.
Yes, that's right. If I choose a particular angle of incidence in the denser medium, yes, I will be able to face a scenario where the refracted ray will exactly pass along the boundary. Are you guys able to visualize? So this is first refracted ray, second refracted ray. Maybe this is the 10th refracted ray. You're doing this experiment, you're increasing. Okay, but my question is this 10th refracted ray possible or not? There will definitely be one situation where you keep increasing the angle of incidence. The angle of refraction is also increasing on the other side in such a way that at one particular scenario, you can say that when the angle of incidence is I, then the refracted ray will exactly pass along the boundary of both the medium. Are you able to understand this? And why is it happening? It is purely happening because in this scenario, the ray is getting bent in the clockwise direction. Tell me yes or no.
Yes, sir.
Yes, sir.
Right? Now my question is, what will happen if you increase the angle of incidence So let me call this angle of incidence according to the experiment is the 10th reading of your experiment. What will happen if you increase the angle of incidence beyond your 10th reading? Means if you increase it even more, the ray will get bent, the refracted ray will get bent more in the clockwise direction. So what will happen to the refracted ray?
Move inside the diameter.
It will move inside. Means there will occur a scenario where the ray, instead of getting refracted, it will get reflected back into the same medium. Since this is happening internally, we call it as internal reflection. And the most important point is, unlike the reflection that is taking place with respect to mirror, this reflection is 100% efficient in the sense all the rays will get bent back into the same medium. The loss of energy is not there. Are you able to understand? That is the reason why we use the word total. So it is not like normal reflection. What exactly is happening? There is one particular scenario where the refraction concept is actually getting converted into reflection, and it is happening internal to a given medium. And this kind of a phenomenon is possible under what scenario? Is it possible whenever the light rays?
Denser to rarer.
Yes, that is so. Always when you're giving a definition to it, you need to start with the term when a light ray is traveling from denser to rarer medium. Okay, after that only you need to write whatever definition you're going to give. Okay, I hope I'm clear with this. So I'm going to give you two definitions. Observe. So I told you, the 10th reading is there where the refracted ray is exactly moving along the boundary. So what is the angle of refraction?
90
It
degrees.
is 90 degrees, right? So this angle of incidence in the denser medium, for which the angle of refraction in the rarer medium is 90 degrees, is called, any idea about what is the name of this angle of incidence?
Critical angle.
That's right. It's called critical angle. Okay. Now this is the first term that we are going to see before total internal reflection. So write down the heading as critical angle. When a refracted ray, when a ray is traveling from denser to rarer medium, when a ray is traveling from denser to rarer medium, the angle of incidence in the denser medium, for which the angle of refraction is 90 degrees, is called critical angle. critical angle, and it is written as IC or C. That is the symbol that we use. Okay.
So can you repeat the definition once, sir?
Yeah. From where? From
Sir,
which point?
after radar medium, the angle?
Did I say the angle of incidence in the rarer medium? What did I say? Angle of refraction in the rarer medium is 90 degrees. Did you write the angle of incidence in the denser medium?
No, sir. No, sir. From
Okay, I'm repeating again. Listen. When a ray is traveling from denser to rarer medium, the angle of incidence in the denser medium, for which the angle of refraction in the rarer medium is 90 degrees, is called critical angle. Okay. So if I say the refractive index of the denser medium as mu1 and the refractive index of rarer medium as mu2, then what is the relation between mu1, mu2 and sin I? Sin IC. If this is IC, this will be the refracted ray. This is mu1, this is mu2. So mu1 into sin IC is equal to mu2 into sin how much? 90 degrees.
90.
So sin IC will be equal to mu2 divided by mu1. So IC will be equal to sine inverse of mu2 divided by mu1. Special cases, if mu2 is 1 and mu1 is mu, then IC will be equal to sine inverse of 1 by mu. I'll not suggest it as a very big formula because you can derive it in no time. Maximum 5 seconds you can derive this. Okay. So, but remember the method of deriving. Okay, it is sine inverse of 1 by mu. I hope it is clear. Then, can someone give a definition for total internal reflection? So, what is the definition for total internal reflection? When a ray is traveling from which medium to which? Obviously, denser to rarer.
And
When?
incident,
Yeah, incident at what angle?
angle greater than the critical angle.
That's right. When the angle of incidence is more than the critical angle, the phenomenon, why I'm using the word phenomenon is because you can see it. The phenomenon where the light ray bends back into the denser medium is called total internal reflection. When a ray is traveling from denser to rarer, when the angle of incidence is more than the critical angle, the phenomenon where the light ray bends back into the denser medium is called total internal reflection. Okay. So there is a topic called optical fibers, which is an application of TIR. This one I'm giving it as self-study because it's full of theory only. So you need to read what an optical fiber is made up of. It has a core cladding. Okay. So when the light rays are traveling from denser to rarer, this total internal reflection will take place, as a result of which the data will be transferred from one place to another. So this is actually a very simple concept and small concept. You can read it from textbook. If you have any doubt, you can let me know. Okay, I'll mainly concentrate on derivations part. So whatever applications of TIR are given in your textbook, you go through it. The next concept that we are going to see is, we have completed the concept of refraction at plane surface. Now we'll be talking about refraction at spherical surface. Okay. Just like how we saw reflection at spherical surface, spherical mirrors, we will see refraction at spherical surface. Okay. So let's say we have a refracting spherical surface. Okay. Now, what I'm going to do is, we'll place a point object at this place. I will take this scenario. I'm placing a point object here. Now I'm asking you to complete the ray diagram. So how will you do this? So this is O. Let's say this is the center of curvature. Let's call it as C. Now tell me, how will you complete the ray diagram for this?
To draw the object.
Yes. So we have drawn the incident ray. Object is point object in this case. Okay. So what is it we need to do? We have the point of incidence. I told you. At the point of incidence, we need to draw the, what do we need to draw? Normal. And the normal will always pass through the center of curvature. Right? Now tell me what you have. Yeah, tell
We
me.
need to mention if it's a concave or convex.
It is a concave, no? Object is placed on the concave side. So object is obviously on the concave side. But there is one more question you should ask. What is it?
Denser or rarer?
Yes. Since you're talking about refraction, refraction is going to happen between different medium. So medium is, there is going to be refractive index. If I take this as mu1 and this as mu2, I'm saying mu1 is less than mu2. Then what will happen? So indirectly, what am I trying to say? Ray is traveling from?
Rarer to denser.
It's traveling from rarer to denser, meaning this would have been the actual path and this is the normal, right? I'm repeating it again. It is the actual path and this is the normal. So what will happen to the refracted ray? Since it is traveling from rarer to denser, it starts bending towards the normal.
Towards the north.
Okay. When it is bending, let me draw a clear diagram because. So till this, the concept is clear, right? I hope no doubt.
Yes, sir.
So let me say this is the object. Let's say this is the center of curvature. I will take it like this. This is the actual path. So the ray will get bent towards the normal. So this is one ray. This is one refracted ray. Okay. So let's say this point is A. Now tell me what is the angle of incidence? Tell me in terms of AOCP. Angle OAC is how much? You need to concentrate. So what is the angle OAC? That is the angle of incidence. Because what is the angle of incidence? It is the angle between the incident ray and the normal, right? Then what is the angle of refraction here? I hope you are able to visualize this. Okay. So when I say ray diagram, you need two rays. One ray we have considered from O to A, and we saw what is happening to it. What is the other ray you can consider? What is the other ray you can consider, guys? Are you able to hear me or not?
Yes, sir.
I'm asking what is the other ray you need to consider?
And one below the principal axis.
One below the.
Principal axis.
Between O and C, sir.
You can take it between O and C. You can take it along OCP itself. No? You can take it along the so-called principal axis. So when you consider the other ray like this, at the point of instance, if you draw the normal, it is going to pass through C. So if you take the ray OCP, right, what is the angle of incidence?
0.
0.
So what will be the angle of refraction? That will also be
0.
3.
right? So is there a possibility for the second refracted ray and the first refracted ray to meet?
No.
Then what kind of an image is formed?
Virtual image.
It is a virtual image. Okay, provided the ray is traveling from rarer to denser, and here the refractive index is mu1, and here it is mu2. I hope these things are clear. These are all very, very important points. Okay. Now observe, if I take this angle as alpha, this angle as beta, and the other angle as theta. Okay, we are going to derive an expression which shows the relation between mu1, mu2, the object distance, the image distance, and the radius of curvature. Okay, our expression will have mu1, mu2, u, v, and r. So that is a concept called as refraction at spherical surface. So I told you in this chapter, what is the first assumption we take with respect to spherical surfaces?
Aperture is a straight line.
Yes, that's right. Aperture is small. So when the aperture is small, what happens to the angles? When the angles are small, sine
Sine
of
is equal to tan.
angle is approximated to the angle is approximated to tan of
Tan.
angle. Okay, I hope these points are clear. So wherever refraction is involved, you should by default start with Snell's law only. So when I apply Snell's law, at which point?
P.
At A. If you apply P, you will not get anything because there are no proper angles. Angle of incidence is 0, angle of refraction is 0. So when you apply it at A, you can say mu1 into sine I will be equal to, tell me.
mu2 into sin r.
That's right. So mu2 into sine r. From here, I can write mu1 into I is equal to mu2 into r, since angles are small. Accepted? First. So what did I tell the expression? The final expression will consider, will have in it. You will have refractive indices, object distance, image distance, and the radius of curvature. All these are distances. So wherever distances are involved, what they say?
Tan.
You need to look for tan. So if you need to look for tan, you need to start looking for right angle triangle. But what is the assumption we have already made? The aperture is very small. When the aperture is very small, we can say AP is approximately a straight line, because all the rays that you have considered are marginal rays. They are close to the principal axis. Am I clear on this?
Yes, sir.
right? Now see, I'm going to consider what is tan alpha. What is tan alpha? Tell me. So what is the right angle triangle that involves, if I take AP as right angle triangle, if it is like this, then what is the right angle triangle we need to consider for including angle alpha?
OAP.
OAP.
Angle APO. Ensure that your right angle is at the center. This will be alpha. Okay. So from triangle OPA, what is tan alpha?
AP by
AP
OP.
divided by how much term?
OP.
OP. AP by OP is minus.
U.
Why am I
U.
writing minus?
Sign convention.
Sign convention. Minus U. Let this be 2. Next. From triangle. What is the other angle you are able to see on the base? Beta. So if I need beta, which triangle should I involve?
API.
Yes. So if I take triangle API, then tan beta will be equal to how much? AP by AP divided by PI. Again, it is AP divided by PI is how much?
Minus V.
That's right. So 3. I need tan theta. Triangle
AP by R.
APC. From triangle APC implies tan theta is equal to AP divided by minus R. So this is 4. Remember, since the angles are small, what is the approximation we can do here? This will be approximately alpha, this will be approximately beta, and this will be approximately theta. Let this be 2, 3, and 4. Go through this. Is there any doubt in any of these steps? Shall I proceed?
Yes, sir.
Now see, I'm going to consider certain triangles. If I take triangle OIA, if I take triangle OIA, angle the line OA is making an angle alpha with the x-axis. So this angle is alpha. If I project it, this will be beta. Then what is angle IAO? So what is angle IAO, guys?
Beta minus alpha.
No, this is I. No, according to the diagram.
Oh.
Look at the diagram. No? This is I. Yeah, it is just I. So we know that exterior angle is equal to sum of opposite interior.
Sir, you are not audible. Sir.
Beta is equal to alpha plus I.
Sir, your mic is very, very feeble, sir.
Yes, sir, you're not on. Is it better now?
Yes, sir.
Yes, sir.
Yeah. So beta is equal to alpha plus I is equal to beta minus alpha. Let me take this as equation number 5. Okay. Now what I want you to do is tell me what is R similarly. For me to involve R, if you observe, see, I'm taking this angle as R. Then how much will this angle be?
R.
R.
It is all vertically opposite angles. So for me to involve R, beta, and theta, what is the triangle I need to consider?
AIC.
So if you consider the triangle, this is A, right? I, C, then this is theta, this is beta, and this is R. So from triangle AIC, theta will be equal to beta plus r, which implies r will be equal to theta minus beta. Let this be number 6. So is there any doubt in this?
No, sir.
Okay. Now what we are going to do is, using 5 and 6 in equation number 1. So where is it? The first equation is mu1 into I is equal to mu2 into r. Mu1 into I is equal to mu2 into r. Mu1 into what is the value of I? It is beta minus alpha is equal to mu2 into r is theta minus beta. Okay, I'm rearranging the equation. Observe, beta into mu1 plus mu2 is equal to mu2 theta plus mu1 alpha. Concentrate, guys. There's a very, very important derivation. Most of the time, this comes in the 5 marks one. So beta into mu1 plus mu2 is equal to mu2 theta plus mu1 alpha. So what is the value of beta? AP by minus V is equal to mu2 into what is theta?
AP divided by
By
R.
minus r.
Minus R plus mu1 into alpha is AP divided by minus U. So minus is cancelled. AP is cancelled. Mu1 plus mu2 divided by V is equal to mu2 by R. 1 minute. That is mu2 by V minus mu1 by U. mu2 minus mu1 by R. Wait just a minute. AP by U, AP by V.
Sir,
Yeah.
sir, in triangle AOI, the whole
Huh?
angle is not I, sir. In the down,
Yes,
sir.
sir. That whole angle is not I, sir. OAC is a I, sir.
OAC is I. Then what? I took AOC only, no?
No, sir. AOI, sir.
No, sir. We assume
Okay.
OAI, sir.
Then yeah. Then this should be I minus R, right? So where is that step OAI? Then this angle should be I minus R, correct?
Yes, sir.
Should be I minus R. Then beta will be equal to how much? Alpha plus I minus R. So beta is equal to alpha plus I minus R. In the place of minus R, can I write it as theta minus beta? Did you understand what I did? I'm using the reverse logic. So R is theta minus beta. So beta is equal to alpha plus I minus theta. Okay. Beta is equal to alpha plus I minus theta plus beta. This and this will get cancelled. So what is the value of I? I is equal to theta minus alpha. Accepted? You're able to understand what I did? So again, the same thing. Beta is equal to alpha plus I minus R. I plus alpha plus I minus, in the place of R, I use theta minus beta. Then beta and beta got cancelled. Then I will be equal to theta minus alpha. Right? So using that here, what do we get? Mu1 into what is the value of I? Theta minus alpha is equal to mu2 into what is the value of R? Theta minus beta, which implies mu2 minus mu1 into theta is equal to mu2 beta minus mu1 alpha. Right? So mu2 minus mu1, what is the value of theta, guys? AP by minus R. Right? Is equal to what is mu2 into beta? AP by minus V minus mu1 into AP by minus V. Okay, minus gets cancelled. AP is gone. So what is it you're left out with? Mu2 minus mu1 divided by R is equal to mu2 by V minus mu1 by U. This is the required expression. So this is the required expression that you need to remember.
Sir, how mu2 minus mu1 into our theta, sir?
I rearranged it. You solve this,
Okay,
you'll
sir.
get it.
Okay, sir.
You would understand. So this is the final expression that we need to remember. So if you don't use sign convention, what would have happened is you would have got a specific condition in this case. Then there are different scenarios possible, right? What would have happened? What is the scenario that we have taken here? The first medium is rarer medium and the second is denser. What if I swap it? Then you would have got a different expression had you not used the sign convention. But if you use the sign convention, what will happen is you will get the same expression. Mu2 minus mu1 divided by R is equal to mu2 by V minus mu1 by U. So this is an expression that you have to remember. I'll tell you how to solve this problem. Solve problems based on this. So let's say there is an object which is placed at a distance of 10 centimeter in a medium whose refractive index is 1.25. Okay. Now, medium of refractive index 1.25, radius of curvature is, let's say, 5 centimeter, and the refractive index of the second medium is taken as 1.3, or let's take it as 1.5. Find location of final image. So how to solve this? The formula is mu2 by V minus mu1 by U is equal to mu2 minus mu1 by R. This we have derived using the sign convention. Right? So mu2 is how much? 1.5 divided by the final image is what you need to find. So whichever is unknown, you should not use sign convention to it. Minus mu1 is how much? 1.25 divided by U is
minus 10.
Minus 10.
is equal to mu2 minus mu1. That is 1.25 minus 1 divided by R is minus 5.
5.
Minus
1.5 minus 1.25, right? By minus. So how much will the answer be? 1.5 divided by V. plus 0.125 is equal to 1.5 minus 1.25 is 0.25. 0.25, yeah. 0.25 divided by minus 5, that will be minus 0.05. So 1.5 divided by V is minus 0.05 minus 0.125. So what will be the answer? 10, 3. So 130, right? So that is 1.5 divided by V. V will be equal to so if you multiply these two values, you will get the final image minus of something centimeter. But what does this minus sign indicate here?
It's in left side of the.
It is on the left side, means it is a virtual image. Okay. So we are trying to say that it's a virtual image that is formed due to this kind of scenario. I'm going to give you another question, solve it. So what we are trying to say here is there is an object which is placed on the convex side of the refracting surface. It is based on the convex side of the refracting surface, where the refractive index of the medium is 1.5. Okay. The refractive index of the other medium is 1.8. Okay, I'm taking it in this way. Now you need to locate the image position. I'll give you 2 minutes time, do it. So how to proceed? Mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by R. So here, instead of remembering mu2 and mu1 as right side and left side medium, you can remember like this. Mu2 is the medium where the image is formed. Mu1 is the medium where the object is formed. So mu2 minus mu1 divided by the radius of curvature of that particular surface. So mu2 is 1.8 divided by V minus mu1 is 1.5 divided by U is how much? Minus 2 is equal to mu2 minus mu1, 1.8 minus 1.5 divided by what?
5.
It is only 5 because the radius of curvature will be on the right hand side. Right? So 1.8 divided by V plus 1.5 divided by 2 is 0.75 is equal to 1.5 minus 1.8 is 0.3 divided by 5. So 1.8 divided by V plus 0.75 is equal to 0.6 or 0.06. So calculate what is the final value. You will get as a negative value. So negative value indicates that here also the image formed is virtual.
2.6, sir.
I don't know the value. I just randomly gave.
Okay.
Are you getting minus 2.6?
I also don't know that, but 2.6.
But you told 2.6.
I'm not sure about it, sir, but I got that answer.
Okay. That is minus 2.6. But I hope you all understood how to solve the problem, right? And you understood when to take sign convention. So you need to take sign conventions only for distances which you are sure about. The distances which you are not sure means distances which are unknown to you. You are not supposed to apply sign convention to it. The problem will take care of it. Okay. So this is all about refraction at spherical surface. Then we have the concept of lens, prism, and optical instruments. So with that, this chapter is over. The next class I will start lens. Okay, but for you to understand lens, you need to be clear with this refraction at spherical surface. I am not proceeding because this concept is slightly tricky. I suggest you all to practice properly. Okay, so if possible, I'll give you an assignment which is based on this topic. Already there is an assignment pending from my side. I will give it. So I will try to give an assignment based on this. You can complete it before the next class so that you can understand the remaining topics clearly. Okay. So just wait for a minute.
Sir,
Yeah, tell me.
sir, the R is positive because it is in the right side, sir.
Yes. For a